Hi, welcome back to the channel. I know we're used to solving problems to end with figures like 2, 3, minus 1, pi, even 8,000, minus 1 million. These are all real numbers. In today's lesson, we'll be seeing how to work with problems that end with square root of minus 8, square root of minus 100. These are minus 1,000. These are referred to as complex numbers. I will use an example to help us understand how to work with. I will use an example to introduce us to complex numbers, and at the end of this lesson, I will also give you a take-home example that can help you understand it further. That said, let's get into class. If you have a sum like if you have x squared plus 3x plus 2 is equals to 0. This is actually a quadratic equation, and we can easily solve this using our formula method. In case you missed our lesson where we explained how to solve quadratic equations using formula method and completing the square method, please do not hesitate to check the description below where we'll place a link to our lesson. Now, from our formula method, we know that x will be equals to minus b plus or minus square root of b squared minus 4ac all over 2a. So that in this function, we'll be saying that our a will be equals to 1, our b is equals to 3, and obviously our c is equals to 2. So that my x in this case becomes minus b will be minus 3 plus or minus square root of b squared, that's 3 raised to the power 2, minus 4ac, a is 1, into c is what? Is 2, all over 2a. So that my x now comfortably is the same thing as minus 3 plus or minus, by the time you expand this should lead us to 9 minus 8. 4 times 2 is 8, all over 2a. That's 2. A is 1. So that x now obviously is the same thing as minus 3 plus or minus square root of 1 over 2. Now this is minus 3. X obviously is equals to minus 3 plus or minus, that's plus square root of 1 is 1 plus 1 over 2, or minus 3 minus 1 over 2. So that x obviously is the same thing as minus 3 plus 1, that's minus 2 over 2, or minus 3 minus 1, that's minus 4 over 2. So that x is equals to minus 1 or minus 2. Now, if you look at these figures carefully, these are all real. They are real numbers. But let's take another example. If we have this equation that says 5x squared minus 6x plus 5 is equals to 0. Now, if I'm to solve this using x is equals to minus b plus or minus square root of b squared minus 4ac over 2a, here a here will be the same thing as 5, my b here will be the same thing as minus 6, and my c here will be the same thing as 5. So that my x now will be the same thing as minus 6 plus or minus square root of b squared, that's minus 6 all squared, minus 4, a is 5 into 5, and c again is 5 into 5, all over 2a. 2a is 5, a is 5, so 2a will be 10. So that x obviously will be the same thing as minus 6, that's plus 6, plus or minus square root of minus 6 all squared, that will be 36, minus 4 times 5, that's 20, 20 times 5, that's 100 over 10. So that x now will be the same thing as 6 plus or minus square root of minus 64. Minus 64 over 10. You agree with me that solving the square root of minus 64 can be a lot challenging. So this leads us to what we've been talking about, which is our complex numbers. So that as complex numbers, for our complex numbers, if I have the square root of minus 64, I can express the square root of minus 64 to be the same thing as the square root of minus 1 times the square root of 64. So that this becomes, now for the square root of minus 1 in complex number, I'll say j, will express it as j. J is the same thing as minus 1. So if j is minus 1 and the square root of 64 is 8, this j is the square root of minus 1, it becomes j, so that the root of minus 64 can now be expressed as j times 8. So I can express it as j8. So as complex numbers, x now will now look like x is equals to 6 plus or minus j8 all over 10. X now will now be the same thing as 6 over 10, that's 0.6 plus or minus 0.8, j0.8. Now this is a complex number. Like a regular numbers, we can express our regular numbers in the form of Cartesian coordinates. You remember your Cartesian coordinates, you can express your regular numbers as in your Cartesian coordinates, where we have our y-axis and we have our x-axis. The same thing applies to our complex numbers. I can express my complex number in the terms of a complex plane where I'll have my real axis, you have your real axis, and also you have your imaginary axis. You have your imaginary axis. Now on the imaginary axis, we have the complex part, and on the real axis, we have the real part. A good example is my minus 8 and 10, and is my minus 6 is 6. Let me see that solution. A good example is 0.6 plus or minus 0.8. Now let's express this in our Cartesian coordinate. We have it as 0.6 plus j 0.8, or we have it as 0.6 minus j 0.8. Now, for the first one, which is 0.6 plus j 0.8, I'll have my 0.6 on the real part. If this is my 0.6, then I'll have my j 0.8 on the imaginary part. So I can locate my points. Let's say this is equals to z. If this is equals to z, so comfortably, I can locate my point z between the positive parts. This is my point z. And let's call this one my y. So if this is my y, let's draw the complex plane for y. Now here's my imaginary part, and obviously here's my real part. Now here again I'll have my 0.6, but because I'm having my j in the negative axis, I'll have my j below. I have my j here. That's the 0.8 in the negative part. So we can locate our negative point below. Here is our negative point. So I have this as my y. So with this, I have been able to explain how to solve. I believe with this, we've introduced our complex numbers, and in subsequent lessons, we'll be working more on complex numbers. Like I did promise initially, that I'll be giving you a take-home assignment or a work example to help you understand how to come up with complex numbers properly. Now if we have x squared minus 6x plus 34 is equals to 0. Now do solve this equation, and let's see both the real part and the complex part in the comment section. Thank you for staying with us, and do have a nice day.